Okay, in this lecture we're going to continue our work on the method of undetermined coefficients and discuss in more detail how to choose the correct form for the particular solution of our non-homogeneous equation. In some of our earlier examples, we've seen that the initial guess for the form of the particular solution wasn't correct, and we went back and had to modify that initial guess. So let's discuss in full detail how to choose that correct form for the particular solution from the beginning. This is, of course, one of the more challenging parts of this method is choosing that correct form. So here we were considering a non-homogeneous equation of the form shown here, a second-order linear non-homogeneous equation with constant coefficients a, b, and c. So let's look at some different types of functions, g of t, for which we can use this method of undetermined coefficients. The first type that we looked at in case 1 is if g of t is an nth degree polynomial. Then we would consider a particular solution of the same form. That is, let us look at some general nth degree polynomial. And this will be the correct form for the particular solution unless 0 is a root of the characteristic equation. If 0 is a root of the characteristic equation for the corresponding homogeneous equation, then part of our homogeneous solution would involve a constant times e to the 0, or that is a constant. And since a constant term already appears in our particular solution, we would have to multiply that initial guess by a factor of t. And in general, we would multiply by t raised to the s power, where s is the number of times that 0 was a root. So for instance, if 0 was a repeated root of the characteristic equation, our homogeneous solution would have the form c1 plus c2 times t. So I would have a constant and a linear term. And so my particular solution would then need to involve a quadratic or higher degree term. So I would multiply my nth degree polynomial by a t squared. And so on, where in general we multiply by t to the s power, where s is the multiplicity of the root 0. Now, the next case that we will consider, or that we had considered in our examples, was if g of t is some nth degree polynomial times an exponential, e to the rt. In which case we would look for a particular solution of the form some nth degree polynomial times the same exponential, e to the rt. And this will be the correct form of the particular solution unless the exponent, e to the rt, already appeared in our homogeneous solution. So as long as the value in our exponent, r, is not a root of the characteristic equation, then we don't have to multiply by a factor of t out in front. We might consider that multiplying by t to the 0, or just 1. However, we've seen that if r was a root of the characteristic equation, that is, if e to the rt already appears in the homogeneous solution, we would have to multiply by t. So if r would be a simple root, that is a root of multiplicity 1 of our characteristic equation, we would have to multiply our initial guess for the particular solution by a factor of t to the first power. Similarly, if r would be a double root or repeated root of the characteristic equation, then we would also have within the homogeneous solution a term involving t times e to the rt. And so I would have to multiply my initial guess for the particular solution by t squared. So depending on which terms appear in our homogeneous solution, we would have to modify our initial guess for the particular solution by multiplying by a power of t. And then the last case that we consider for the method of undetermined coefficients is if our g of t function involves some nth degree polynomial times an exponential times a sine or a cosine function. In which case we would look for a particular solution of the form some general nth degree polynomial times the same exponential, e to the alpha t, times the same sine function, sine of beta t. And we saw that we also had to include the same sort of thing, but with a cosine function. So we would have then some nth degree polynomial times the same exponential times cosine of that beta t value. And this would be the correct form for our particular solution unless these terms already appear in our homogeneous solution. And the only way that these terms would appear in the homogeneous solution is if we had complex conjugate roots of the characteristic equation. So as long as alpha plus or minus beta I are not roots of the characteristic equation, then we don't have to multiply by a factor of t out in front. In other words, we would multiply by t to the 0, or just 1. But if alpha plus or minus beta I was a root of the characteristic equation, then these terms would already appear in the homogeneous solution, and we would have to multiply by a factor of t out in front. So essentially, we're making a guess about the form of the particular solution where we would consider the same general form as the g of t function, unless that term already appears within the homogeneous solution, in which case we have to multiply by a power of t out in front. So let's consider an example of choosing the correct form of a particular solution for a non-homogeneous equation. In this example, we're asked to find the form of our particular solution where g of t is a given function. We'll consider several different parts here. Now we know that we first have to consider the solution of the homogeneous equation. So if we were to do a little scratch work to the side here, if we look at our homogeneous equation, it would have a characteristic equation of r squared plus 2r minus 3 equals 0, which can be factored as r plus 3 times r minus 1. And so r could be negative 3 or positive 1, in which case my homogeneous solution would have the form c1 e to the negative 3t plus c2 times e to the 1t. So let's now consider particular solutions if our g of t function was given by these different cases, parts A through F in this example. So in part A, we have a g of t function, which is 7 times cosine of 3t. So that is a constant times cosine of 3t. So for our particular solution, we would consider something of the form some constant, let's say a, and then since we had a cosine of 3t term, we will have to include both a sine and cosine term as part of our particular solution. So we will have a constant times sine plus another constant times cosine. And we don't have to modify this initial guess by multiplying by a factor of t, because neither of these terms appeared in the homogeneous solution. Now in part B, we have a g of t function, which is a first degree or linear polynomial times an exponential e to the t times sine of t. So for our particular solution, we would look for a general first degree polynomial, let's say at plus b, times the same exponential e to the t times the same sine function sine of t. But because we have sine as part of our g of t function, we will also have to include the same sort of expression with the cosine. So let's take another first degree polynomial, ct plus d, e to the t cosine of t. And we would not have to modify this initial guess because we don't have any terms in the homogeneous solution involving e to the t times sine or cosine. Now in part C, our g of t function was t squared, so a quadratic or second degree polynomial, times cosine of pi t. So we would take, for the particular solution, a general quadratic, say at squared plus bt plus c, times a cosine or sine function. We know since we involved cosine, we will have to include both a term with sine and cosine. So here we would have our quadratic times sine of pi t plus some other quadratic, with the cosine of pi times t. And we don't have to modify this initial guess by multiplying by t because our homogeneous solution didn't contain any terms involving sine or cosine of pi t. So let's look at some other ones. In part D, we have a constant times an exponential, e to the negative 3t. So our particular solution, we might consider something of the form a constant, a, times e to the negative 3t, the same exponential. However, we see here that a constant multiple of e to the negative 3t was part of the homogeneous solution. So we need to multiply our initial guess by a factor of t, giving us a times t, e to the negative 3t. And now we see that our homogeneous solution does not contain anything of the form t times e to the negative 3t. So this would be the correct form for our particular solution. Now looking at part E, we would have a linear term, a 3t times e to the 3t. So our particular solution, capital Y, we might consider as a general linear polynomial at plus b times e to the t. But now when we compare this with our homogeneous solution, well, we see that part of our particular solution, a constant multiple of e to the t, already appeared within the homogeneous solution, so we would need to multiply this by a factor of t, giving us at squared plus bt times e to the t power. And then for our last part, we have a g of t function, which is a quadratic t squared times e to the t. So we might initially consider a particular solution, which would be a quadratic times e to the t power. But again, we see that a constant multiple of e to the t was already part of the homogeneous solution. So we need to modify our initial guess by multiplying by a factor of t, giving us at cubed plus bt squared plus ct e to the t. And since none of these terms appear within the homogeneous solution, this would be the correct form for our particular solution.